Good afternoon, pilot teachers, and good afternoon, students. Okay, thank you. Sit down. We are going to spend one more lesson on looking at insolation before we move on to the next topic on climate. And basically for our lesson today, we are going to recap most of what we have covered already on solar radiation and insolation, and also we're going to look at completion of some activities which I have prepared for you. Before we start off with looking at those activities, I'd like us to quickly look at what we have covered so far on the work on insolation and solar radiation. From our definition in our last lesson, we said solar radiation is simply to do with energy from the sun. The energy coming from the sun is termed solar radiation. The amount of solar radiation that reaches the ground or the Earth's surface is referred to as insolation. From what we have covered, we also noted that solar radiation is distributed, and according to the distribution, we have seen that approximately about 15% of all the radiation that comes through is absorbed by the atmosphere. So if we look at the arrow from this particular diagram, you see the arrow coming through, and there is no arrow going back out simply because of the absorbing of the radiation by the atmosphere. 15% absorbed by the atmosphere. About 6% of all the radiation that comes through is reflected back into space by the atmosphere. So here we see that arrow showing that reflection, the radiation coming through but bouncing back or reflecting back into space. We mentioned that it is approximately about 6% that gets to be reflected. About 27% of all the solar radiation comes through the atmosphere, reaches where the clouds are in the troposphere, and then the clouds tend to reflect the radiation back into outer space. So 27% is reflected by the clouds. We have about 2% of the radiation is actually reflected back into space by the Earth's surface itself. And features on the Earth's surface such as such as snow and ice and water also help to reflect some of that, or the 2% back into space. Meanwhile, 50% of the radiation that comes through is actually absorbed by the Earth. That 50% then contributes generally to the heating up of the Earth's surface and the atmosphere around it. You were also required to complete an activity for your homework, and I would like us now to make correction to that particular activity before we move on to doing some more activities mainly to do with insolation and solar radiation. So if you can double check now on the diagram that you have constructed, and you were supposed to copy that diagram into your exercise book. From that diagram, there were squares which were left blank. Using the information that was provided, you were supposed to put in the different units into those boxes to have a complete show of what happens to solar radiation when it comes through the atmosphere to the surface. Okay, so if we look at the activity or the task you were supposed to have done yesterday or in the last lesson, the instruction said you use the information given to help you fill the correct number of units of heat for each arrow shown on the diagram. The information that you had, how the sun hits the earth, the following list explains what happens to 100 units of heat from the sun. 27 units are reflected back to space by clouds. 6 units are scattered in the sky, giving the sky its blue color. 2 units are reflected back to space from the Earth's surface. 50 units heat up the Earth's surface, and 15 units are absorbed by the atmosphere. That information you also made note of, because you will need that information to fill in the boxes on the diagram. Okay, that diagram, and now we're ready for our answers. We give the answers. We'll start on from the left side. We'll work our way down to those 3 boxes, and then the 2 going from here to the top. Bill, your answer then for the first box where it says scattered. From the information given, what would be the unit that should go in this box here?
6 units.
6 units. Do we all agree with him that it is 6 units? Okay, we double check and correct, definitely. So 6 units scattered, giving the sky its blue color. Rebecca, the next box, absorbed. What should go in this box here, or how many units?
15 units.
Okay, 15 units absorbed by the atmosphere. We agree with her that the answer here should be 15. Yes, okay, good. 15 units absorbed by the atmosphere. Christopher, the box here, heat up the Earth's surface. How many units?
50 units.
50? We're happy with 50. Okay, good. 50 units should be the answer for the third box. How many units are reflected? Ovio, the answer that should go in this box here.
2 units.
2 units. All happy that it is 2 units? Okay, good. So here we are looking at 2 units reflected on surfaces such as the water, the land itself, snow and ice, etc. Finally, the last answer for this particular box. Frank, what should be?
27 units.
27, okay, we double check. Frank is correct to say 27 units. And then if we add up all those units, we should come up with 100 units of solar radiation or sun's energy. Okay, we double check and make corrections. This is what you're supposed to have completed for your homework. Any queries or questions with regards to that homework or to the work we've covered on insolation and solar radiation? No questions? Okay, 2 more questions I'd like you to work on if there are no questions from the class. See if you can have the answers quickly, and then we'll go through the correction. The first activity was simply filling in the diagram. The second one now, the second question I'd like you to answer would be, how many units or how many of the 100 units are reflected back to space? You have to make reference to your diagram for you to be able to answer this question. Question 3, how many units are left to hit the earth and the air? Your answer also will come from the diagram and the information you made note of in our last lesson. I'll give you 4 minutes for the completion of those 2 activities. You can discuss with the person sitting next to you, come up with your answers, and also have your answers written in your exercise book. How did you get your answers, 35? Okay. Is this absorbed by the clouds, or is it absorbed by the atmosphere? By the atmosphere, because the reflection here, this is the one by the clouds. Okay, so you could be correct, definitely. Second question. Why did you come up with the answer 29?
Heat that is reflected from Earth's surface also moves back to space, and the one that is reflected by the cloud also moves back to the space. So we say that.
Two together, okay. You could be correct. When we do the corrections, then perhaps your answer might be correct. Okay, work on the second one. Your answer is the same, or your explanation would be the same. Okay. You got your answer for the two questions? But you have answered both questions 2 and 3? Okay, most students have got their answers then for those two questions, so we'll correct. Okay, correction then to those two questions. The first one, Anita, how many of the 100 units are actually reflected back to space? The 100 units, we are making reference to this particular diagram here, the diagram that you copied in your last lesson. So how many of the 100 units that are coming through are reflected back into space?
29
Can
units.
can you explain to the class why or how you got 29?
Because there are only 27 units reflected back to space by the clouds, plus the 2 units that are reflected back to space from the Earth's surface. The rest of the units are scattered and absorbed.
The rest of you, do you agree with her explanation? Yes, definitely. Anyone else with a different answer beside 29? What answer did you get? Mason, did you get 29? Gao, did you get 29? No? Dorothy, did you get 29? Besides Gao not getting the answer 29, who else did not get 29? Okay, those 3 students at the back. We double check. Anita's explanation on the reflected 27% or units and the 2% is definitely correct. When we look at scattering, do the units reflect also from the process of scattering? Do the units reflect also from the process of scattering? If you are saying yes, then you should add that 6 to the 29. If you are saying no, then we'll have to come up with the definition to what scattering is. What do you think is the word, or what is the definition that we can give to the word to scatter? To scatter is to spread. How about to reflect? To bounce back. Wouldn't the process of scattering and reflecting be about similar? Both are coming through, but then are scattered or reflected back. And that is the reason for why I am now saying that our answer should be 27 plus 2 plus 6 to come up with a total of 35 units. So you make your corrections. If you have 27 or 29, the correct answer should be 35 units. Hands up those students who had 35 units. Okay, the 3, 4 plus Gao, 4 students in the class, well done. Okay, the next question. The next question. How many of the units are left to hit the earth and the air around it? Shelley, what is your answer for this question here, question 3? How many units are left to hit the earth and the air around it?
65 units.
65 units. Can you explain how you got 65 units?
The 50%, the unit from the 100 units hits at the Earth's surface, and the 15%, which is absorbed by the atmosphere, is added to the 50 to become 65.
Okay, very good. So we're looking at the 15% that is absorbed by the atmosphere, because the atmosphere is the air around the earth. We came up with a definition when we were looking at the activities on definitions, plus that 50%, which is insolation. We add those together, and that should give us the 65%. We double check. Are we all happy with the answer 65% for that question? Everyone? Okay, good. That then will be our answer for those 2 questions. We move on. This time, I would like us now to make reference to the handout which was distributed. And the handout contains some more information based on what we have covered on solar radiation and insolation. You have 2 diagrams which are on the monitor. From the 2 diagrams, we'll have explanation to go with those diagrams. And when you look at those diagrams, the diagrams should be very similar to the 2 diagrams we have looked at already. The 2 diagrams we have looked at, one is a secular diagram that shows us the distribution of solar radiation. And the second diagram is the one you copied into your exercise book when you were doing the activity or exercises. And that diagram shows the same thing. Similarly, the 2 diagrams that we are going to look at in our lesson today also will show the same information, but then different ways of presenting the same information. Let's look at the reading from the handout, and then there will be 2 activities that I would like you to complete from the monitor. More information on solar radiation and insolation. We know already that electromagnetic radiation from the sun interacts with gas molecules in the atmosphere by absorption and by scattering. In absorption, which is usually a selective process dependent on wavelength, a molecule takes up radiant energy and converts the energy to different form. In scattering, which can occur for any wavelength, gas molecules divert beams of solar radiation into other directions. So we come back to what we have just covered on reflecting and scattering. Does that information now confirm what we have just looked at on we need to put the scattering together with the reflecting? Yes, okay. Because of scattering, the Earth's surface receives light from the sky in addition to light coming directly from the sun. The moon, in contrast, has no atmosphere to scatter sunlight, which is why shadows on the moon are so harsh. Gas molecules in the Earth's atmosphere scatter blue light much more effectively than red light. So most of the light scattered from the sky is blue. And that is also what gives the sky its blue color. All wavelengths of electromagnetic radiation are scattered to some extent by dust particles and water droplets in the atmosphere, as well as by the gases. But each wavelength of radiation behaves differently in absorption. When long-wave radiation is absorbed by a gas, for example, it causes the molecules of the gas to vibrate. The vibrating molecules collide with one another and heat energy is produced. Energy transferred from long-wave radiation to gas molecules is selective, however. Each kind of gas molecule reacts strongly only with long-wave radiation at particular wavelengths. Water vapor and carbon dioxide are the principal observers of long-wave radiation. That is to do with wavelengths which are greater than 4 microns. But because the sun's surface temperature is so high, most of the radiation from the sun is at wavelengths less than 4 microns, which is too short for any molecules in the atmosphere to act as effective absorbers. As we shall see later, nearly all the radiation that is absorbed by the Earth's atmosphere comes not from the sun, but from much cooler terrestrial surfaces, which are the major sources of long-wave radiation. The wavelengths of visible light are even shorter than those of long-wave radiation. Therefore, no molecule in the Earth's atmosphere can absorb visible light effectively. Visible light, therefore, travels long distances through a clear atmosphere without losing much energy through absorption. Ultraviolet radiation is energetic and often transfers sufficient energy to a molecule to rearrange its structure or even to break the molecule apart. Ultraviolet light is harmful to living organisms because it can disrupt the complex molecules required for life processes. Fortunately, little ultraviolet radiation actually reaches the surface of the Earth. Most of it is filtered out in the upper atmosphere. In the outer layers of the Earth's atmosphere, molecular oxygen strongly absorbs ultraviolet light with wavelengths shorter than 0.2 microns. The ozone layer strongly absorbs ultraviolet light with slightly longer wavelengths, which is between 0.2 and 0.3 micron. And the absorption of energy in the upper atmosphere and in the ozone layer heats these layers to temperatures comparable to ground level temperatures. With the exception of ultraviolet radiation, then, most of the incoming solar radiation is able to pass through a clear atmosphere and reach the Earth's surface. However, water vapor and carbon dioxide molecules absorb most of the long-wave radiation emitted by terrestrial sources, and this absorption has profound effects on the energy exchange between the Earth's surface and the atmosphere. Let's look at the diagram, which is actually on the monitor. And that diagram on the monitor basically shows us the same information on what happens to 100 units or to 100% of the sun's solar radiation that comes through the surface. So if we look at that diagram, you can make reference to your worksheet or the handout also. Similarly, from the sun, if we're looking at 100% of solar radiation coming through, along the way, you would have noted that certain portions or percentage of it gets to be absorbed, others get to be reflected, and others come directly to the surface to heat up the Earth's surface. Here we are looking at shortwave radiation coming through. There must always be a balance in the heating of the Earth's air and the surface. And therefore, whatever comes through also will have to be balanced with whatever goes out. So if, say for example, 50% comes through to the surface, 50% will also have to be sent back or reflected back. So there is always a balance in the heating of the Earth's surface. Imagine if there is no balance, then the Earth's surface might be a little bit too hot. Or imagine if everything lives, then the Earth's temperatures and the surface might be too cold. But because of the balance, the temperatures are kept at a constant temperatures right throughout. The second diagram shows the long wave radiation, and that is what is actually being reflected and scattered and sent back. So if 100% is coming through, 50% is insolation, the other 50% then will have to be sent back, so there is always a balance maintained in terms of solar radiation. With that information, we now have some more activities that I'd like us to work on. Activity number 4, we talked about visible light and light that is actually coming through as one of the wavelengths or radiation that is coming from the sun. Here we have a photograph showing reflected light. And this photograph is a photograph of the Earth taken from the Apollo 17 spaceship. So we're in a spaceship, the Apollo 17, and they have taken the photograph of the Earth here. So we're talking about wavelengths, solar radiation, visible light. From this particular diagram, you are then required to answer the 3 questions. The first question, which part of the Earth here, as shown by the photograph of the Earth taken from the Apollo spaceship, shows light reflected from the clouds? Perhaps you can tell by indicating which color from this particular diagram. B, which parts are light reflected from the ground? So you look at this particular diagram or photograph here and see if you can identify which colors represent light reflected from the ground. C, what do you think, or which parts shown on this diagram here by the blue scattered light, what do they represent? So what do you think the blue parts from the diagram represent? Those 3 activities you can discuss in pairs, and I'd like you to work on to come up with the answers. First 2 are for you to give the colors.
It's 11P, 11G, and this person.
She's outside. The first 2 questions will require you to give the colors. The last question will require you to give a feature. Yeah, you're done. Good. Your answer for that question, blue scattered light. Okay, here goes. Okay, put on. What do you think? What color is showing the light reflected from the clouds? What color from the diagram? This is a diagram of the Apollo spaceship, a diagram of the Earth from the Apollo spaceship. So what color do you think is okay, there, that's the answer. Then you go to the second one, light reflected from the ground. What color from that diagram is light reflected from the ground? Okay, so you have to look at the diagram to be able to come up with it. The third one is the blue scattered light. The blue scattered light, what do you think it is showing? But now you have to write a feature, not the colors. The first two are colors, the last one is a feature. You have your answer? Okay, we'll answer the questions because most students already have answers to those 3 activities. Okay, we start with Ebony. Your answer for the first one. Light reflected from the clouds. From the diagram here of the Earth from the Apollo spaceship, what is the color?
The color is white.
Okay, definitely. All these white areas here will show actually light reflected from clouds. We agree with her that it's the white color? Yes, definitely. Okay, the next question, light reflected from the ground. What is the color? Patrick.
Brown.
The brown, or the brown and a little bit reddish type color that you can see. So here, you see, because these ones here, they represent the continents. This is the African continent. You can see that clearly, the Middle East. So here we are looking at land. So the ground reflects the brown or the reddish type color that can be seen there. Shelley, what do you think the blue scattered light has actually reflected or is showing?
The ocean.
The ocean or the seas, correct. So the ocean is actually represented with a blue scattered light. So our answers again, white, light reflected from clouds, brown or red, light reflected from the ground, and the ocean or the sea is the blue scattered light that we can see. Do your corrections? Okay, your homework now. I'd like you to make note of it. For your homework, to finish off the work on solar radiation, you will be required to construct a diagram into your exercise book showing the distribution of solar radiation. We have looked at 3 possible ways or 3 possible diagrams. One of those diagrams you will find in your booklet, Climate, that contains a circular feature and arrows to show the absorbing of solar radiation, the reflecting, and also the scattering of solar radiation. You can use that to make note into your exercise book or construct into your exercise book. You can use the diagram that we have on the monitor there showing incoming and outgoing radiation, shortwave, incoming shortwave radiation and outgoing long wave radiation. That's the second diagram that you could use to show or to construct the distribution of solar radiation. And the third diagram can be similar to what you have done for your homework, the activity that we did on filling in those boxes. But into your exercise book, you must at least construct a diagram to show the distribution of solar radiation. And that's what I'd like you to complete for your homework. Have you made note of the homework? Okay, good. Okay, class, that also brings us to the end of our lesson. If you can stand up now. To the pilot teachers, our keyword for lesson 94 is short waves. Good afternoon and thank you, students.